Hello, welcome to the Cave Dweller YouTube channel. I'm going to show you today a game that I just started working on that is as big as the Observable universe, as crazy as that sounds. I know I look a little bit like a Jedi, but I am just holding a baby, so you're just gonna have to, deal with that. Okay, so let me show you what it looks like. Alright, so we start by landing on a sphere here, and watching out as other objects fall from above onto the sphere as well. And this sphere is a planet. So basically what's happening here is gravity is being acted on all these objects, including myself, by the sphere. And so I can represent this here by pushing this ball in this direction and watching as it disappears into the horizon. And look at that, there it goes, now it's gone. Now because there's no because there's no friction currently, it's gonna keep rolling forever, all the way until it goes all the way around the planet. And you also might notice that there's a bit of a gap there. That is because the mesh builder I'm currently using builds spheres differently than the collider does. But that's fine, the mesh builder, I'm gonna be making my own mesh builder here soon enough. You can also see how I adhere to the planet's surface when I walk backwards and look at the objects. They disappear into the distance there. And up is a direction that is constantly being redefined, or in other words, I'm being reoriented, so that up is always the opposite direction as the center of the planet. So as I move around, you'll notice the angle of the ground stays pretty consistent because my head is constantly being pointed in a different direction. So now I'm going to show you how these gravitational physics are applied by going into orbit. So I can hit R here to go into jetpack mode and hit space to lift off. And there's my shapes again. And so now in order to get into orbit, I'm gonna align here with where the shadow meets the light. And I'm just gonna go forward and apply some velocity here in the forward direction so I can kind of get my speed up. And now you can see we are orbiting the planet. I don't know if it's a perfect orbit yet. We will find out and see if I hit the ground later or not. But we are definitely going around the planet, and we're going to see that in a second when we see the shapes again. This is probably somewhere around the South Pole. The shapes are on the North Pole, so we'll see them come up in a little bit. And while we're flying, I'm also going to show you here that I can rotate my character. I can reorient my character in this direction. So my roll, I can change my yaw is what that's called, and then pitch is up and down. Look at that, there's the shapes. We're gonna pass them and we're not gonna touch the ground, right? Oh, we barely missed the ground. Oh, lovely. Okay, that was kind of close. I made it kind of close there, but now we're just gonna keep orbiting forever. And look at that, there's that little sphere. He's still going. Go, little buddy. And then I think the only other thing I want to show you here is if I land, boom. My character does reorient itself so that up, once again, because I'm touching the ground, up is away from the planet. And so if I land, on my head, then boom, my character will readjust itself. And that's pretty much it. That's what I got going on. So one of my goals with this project is to build the biggest space game. And I want to do that without loading screens or without unloading a scene and reloading a scene. And I'll have to unload and reload things, but I don't want I want it to be perfectly seamless between solar systems and perfectly seamless between planets, and just all interstellar travel should be perfectly seamless. And in order to achieve this, or achieve really a big space game at all, I had to be careful about what coordinate system I chose. And so the main 3 coordinate systems that are good with larger spaces I have discovered are using 64 or even 128-bit floating point coordinate systems, using the floating origin method, where the player is always centered at 0, 0, and when the player moves, it's actually the universe that's moving around them. And then the third option is something that I was entirely unfamiliar with until doing this research, which is creating a grid. And within each cell of this grid is the host of its own coordinate system. So in other words, the center of each cell has a local coordinate space that starts at 0, 0 for every cell. And then you can determine where you are in space by using the local coordinate system as well as the location of that cell. So in order to properly explain this, let's switch over to a grid. So I want to represent this with a 2D graph because it's easier to demonstrate. So how a traditional coordinate system works is there's an origin called 0, 0. And what that means is it's got a value of 0 on the x-axis and a value of 0 on the y-axis. And if you want a point somewhere that's not at the origin, say, over here somewhere, you would simply input, maybe something like 1500, 1000, something like that. And now we have a point that is 1500 units this way and 1500 units up. Where this gets to be a problem is with really large numbers. Computers are not great at representing numbers that are not whole numbers or decimals. The computer calls these floating points. So to represent that, I'm going to create a really small number here, 1.4 times 10 to the negative 45. That means that's 0 point and then 44 zeros, 1, 4. Now, I'm going to increase this number to the next largest number that the computer can represent. So that's going to be 2.8 times 10 to the 45. That's about double what the previous number was. There's still 44 zeros after the decimal, but there's no number that a computer can represent that are in between those two numbers. This gap gets larger the larger the number becomes. So for example, if we have a really big number like 4 billion, specifically 4,294,967,296, and pay attention to these last three numbers here. The 296, if I increment this number to the next largest number, that 296 becomes 808. We jumped by 512. That means that a computer cannot represent 4,294,000,000 yada yada 297. It can also not represent 4 billion yada yada 296.1. This becomes a huge problem when we are trying to perform physics calculations on Mercury, let's say. 4 billion meters doesn't even make it a tenth of the way to Mercury. And even if it did make it to Mercury, since we're looking at gaps of 512, that means that I'm not going to be able to move a ball on Mercury, let's say, by 1 meter or by 0.1 meters if the origin is at the sun. So instead of representing the world on one coordinate system, or in other words, a system where there's only one origin, 0, 0, my system divides the world into a grid of cells. And each cell, you can think of a cell as like this square right here, for example. Each cell is going to have an origin, 0, 0, of its own at the very center. And so let's say each cell is 2,000 meters by 2,000 meters. That means that if I want to represent this number here, it's going to be something like 500, 0 in the 0, 0 cell. If I wanted to represent this point right here, it would be something like 500, 0 in the 0, 1 cell. And so that means that we have two coordinate systems that are being used simultaneously to represent one point. We have the global coordinate system that identifies which cell the object is in, and then we have the local coordinate system that identifies where in the cell it is. But the advantage this offers is that we don't have to represent super large numbers. In this example, the largest number we have to represent is positive 1000 and negative 1000. And then as soon as we go beyond positive 1000, we are now in the local coordinate system of the next cell. So we never have to deal with large floating point values, which means we can maintain a high level of precision anywhere in the universe. How big can we make it? Well, if we have a grid that is 128-bit indexed, then that means we have access to 3.4 times 10 to the 38 cells. Or in other words, roughly 3 with 38 zeros. So that's way too big of a number to even comprehend. And that's just the width of the grid. Then there's also the height and the depth. So just to put that into perspective, the observable universe is 8.8 times 10 to the 26 meters in diameter. That means that if we take this number of cells and multiply it by 2000, because each cell is 2000 meters, that's going to get us roughly 6.8 times 10 to the 41, or 15 orders of magnitude larger than the observable universe. Now, to be clear, I didn't invent this system, and I didn't even have to implement it on my own. This library right here, Big Space, implements this grid system exactly as I explained it. This video, and I won't show the whole thing, shows how you can represent an object smaller than a proton all the way up to the size of the observable universe. So the map supports really big spaces, but right now my planet is only 2,000 meters across. So it's really small, and I'm not taking, and I'm not using all of that space just yet, but I plan to. Now that being said, I can't make any promises. I do work full-time at Microsoft, and I do have a family I'm taking care of. So who knows where it will actually go, but I just wanted to make this video to show you some of the cool things that I discovered and show you my progress so far. So hopefully you liked it. Thank you so much for watching, and please subscribe if you want to keep seeing more progress videos on this project, and hit like if you enjoyed the video. Thank you so much. Bye.